Hello and welcome to today's Measurement Devices Introduction Tech Talk presented by Swagelok Central Ontario and Atlantic Canada, one of more than 200 authorized Swagelok sales and service centers located around the world in 70 different countries. I'm Tim Phillips, Marketing Manager, and leading today's Tech Talk is our Training and Technical Support Manager, Phil Reid. Before we get started, a few housekeeping items. Please use the live event Q&A feature for all questions. Questions will be answered periodically throughout the session. If you have further questions after the completion of today's Tech Talk, please direct them to Phil Reid, whose email is on the screen, or the technical support team at your local Swagelok Sales and Service Center. We understand through extensive global research and firsthand experience that businesses are under pressure to do more with less, to maximize system performance while juggling smaller budgets, skilled labor gaps, and changing safety requirements. The COVID-19 pandemic only adds to the pressures. Swagelok and its sales and service centers like Swagelok Central Ontario and Atlantic Canada are here to lend a helping hand, to provide you with the right resources at the right time. Swagelok Central Ontario and Atlantic Canada has 3 locations in Mississauga, Ottawa, and St. John, New Brunswick. And we provide local engineering and technical support across our service area of Central, Eastern, and Northern Ontario, as well as all of Atlantic Canada. If you are not located in our service area, there are, as I mentioned, over 200 sales and service centers around the world. So we would recommend reaching out to your local Swagelok Sales and Service Center for any support they can offer. And we're part of an extensive global network here to help you with your applications and share knowledge through our extensive training and system evaluation offering, much of which we are adapting to provide virtually to you. Whether you need help with an application or to improve your knowledge in a specific area, whatever your pressure, think of us as your solutions provider. Now I would like to pass it over to our Training and Technical Support Manager, Phil Reid, to lead the Measurement Devices Tech Talk. Phil, take it away.
Thank you, Tim, and welcome everyone. My name is Phil Reid. I am the Training and Technical Support Manager for Swagelok Central Ontario, Atlantic Canada. I've spent the last 33 years in the Swagelok organization in various roles, and currently I manage a technical support team of field engineers, training, fabrication, assembly services, and other resources. Joining me today to help with the flow is Phil Daniels. Phil is a professional engineer here in the province of Ontario. His focus is in thermal fluids, thermodynamics, and Phil's been with us about 6 years, and here he is dressed going in to do a plant audit, and hopefully we get back to those soon. And Phil's areas of expertise are around hose, advisory services, pressure regulators, systems, high pressure fluid systems, and seal support configurations. And Phil's available in your local area of Ontario and Atlantic Canada to provide help. And Phil's part of a team of global engineers who are readily available to help you with your systems. So what we're going to be covering today is just an introduction to measurement devices. We'll be talking specifically about pressure gauges, transducers, flow meters, and thermometers. But more specifically, we'll be talking about Bourdon tube gauges, elastic element pressure gauges, which are the most common. We'll talk about transducers and how they work. Flow meters, and today's conversation will be around variable area flow meters. We realize there are many different flow measurement devices as well as pressure and temperature. And the temperature thermometers we'll be covering today are Bimetal thermometers. So starting with pressure gauges are covered under ASME B40.100, which is a standard that's a consolidation of a number of other standards. And specifically today, B40.1 pressure indicating dial type elastic element gauges provided by Swagelok will be discussed. We'll talk about diaphragm seals and snubbers. And this standard provides the definitions, the dimensions, safety considerations, the construction of pressure gauges, and this is the standard to which Swagelok gauges are manufactured. And Swagelok gauges are stocked locally at service centers, as Tim mentioned, at 200 various stocking locations around the world and are readily available when you need them. So let's start with what is a pressure gauge. Pressure gauges mechanically sense fluid pressure and convert it to a mechanical motion. And that motion is read somewhere in about a 270-degree arc on the face of the gauge. And it consists of a case and some other elements. But let's take a closer look. If we look at a pressure gauge in a cross section, we see the process connection, which is attached to the fluid pressure source. It travels through to the socket into the elastic measurement element, in this case, which is a Bourdon tube, and we'll talk a little bit more about that in a few minutes. It is attached to an end piece. The end piece is attached to a linkage, which is attached, or linkage or pull rod, which is attached to the movement. And the movement consists of gears, wire springs, and it is a very accurate, precise movement and is calibrated. And these, just like a Swiss watch, these are actually made in Switzerland. And a series of gears which then go to an output shaft, which is attached to a pointer. And that pointer will correlate the pressure indicated along this 270-degree arc, as I mentioned, on the dial. And all of these components are made in accordance with ASME B40.1, B40.100. And if we were to look at that standard, we'd see a picture that looks something like this in a few pages into the document. And it identifies the case, the pressure assembly, the movement, the dial, the pointer, the lens or window, and then the ring that keeps the lens and all of these together. If we look at what the pressure assembly looks like, these gauges, the elastic element in these gauges are a Bourdon tube. And a Bourdon tube is a piece of tube that has been flattened and bent into a C shape. And this configuration is used in pressure gauges from 10 to 1,000 psi. And they would have various thicknesses and various shapes. These are typically in Swagelok gauges, stainless steel. There are some other materials available, but most common in our gauges is stainless steel. There are some Monel Bourdon tubes available as well. But having a little closer look at a Bourdon tube. If you've ever been to a birthday party or New Year's party or an event where you have a party horn, you have applied here to the process connection a fluid pressure. As you apply that pressure, this wrap or Bourdon tube, if we were to fix an end piece to it and connect a linkage to it, as we started to straighten this out, that would correlate to some indication. So the Bourdon tube in an elastic element pressure gauge, this one is a C shape. We can see where we have our process connection here. In this case happens to be a 1/2-inch Swagelok tube adapter. As we flow fluid in, remember this is a dead stop, so it's a pressure indicator. There's no flow in here. So as it starts to try and straighten out this Bourdon tube, the end piece that is connected to the linkage then transfers that mechanical motion to a movement. Moving around to the front of the pressure gauge, we can see that on the gauge, we have a few things I'll point out on this, but we have the pointer, which will indicate the pressure. This is known as a compound gauge. It has positive and negative pressure, and the negative pressure in this case is in inches of mercury or negative kPa. It's also a dual scale gauge. Notice that there's a PSI pressure on the primary scale. The secondary scale in red is in kPa. And other information is on the face of the gauge as well. The 316 wetted components, the increments by which it's marked off are all in accordance with ASME B40.100 as well. The lens and the face. Now that is a that is 10 to 1,000 psi when we have the C shape. Something else I'll mention while we have the back off this gauge, this is a blowout back gauge. So if this were to have a catastrophic failure, the pressure containing components, it would blow out the back, not to the operator or any one of the associates that may be standing in front of this gauge. So 10 to 1,000, we use the C shape. If we go above 1,000, so 1,000 up to around 15,000, for example, we will take a Bourdon tube, and now it becomes helically wound. And this helically wound gauge, it applies pressure, comes through the Bourdon tube, and it tries to straighten it out with much greater rigidity and resistance to the fluid pressure, and transferring that into mechanical motion. So these are helically wound in pressures above 1,000. If we take a look in the back of a higher pressure gauge, we see the process connection to the socket through the helically wound Bourdon tube to the end piece, to the linkage, to the movement. Move around to the front of the gauge again, we see the pointer. This is a dual scale gauge. It has PSI on the primary scale in this case. Now we see bar indicated on the secondary scale. And this is not a compound gauge, so this is reading positive pressure only. Again, noting the internals are indicated on the outside, on the face of the gauge as to what the materials of construction are. And here we see it's a little bit off. This gauge has been taken apart, but the safety lens is in here. And this is a thermoplastic case on this gauge. Looking at a few types of gauges. Typically known as a process gauge is the 4.5 or 6-inch face in that thermoplastic case with a blowout back, as mentioned earlier, if you have a catastrophic failure. Industrial gauges typically made of all stainless steel construction. These are up to a 6-inch face. They down to 40 millimeter, 1.5 inch, and the smaller sizes are up to 160 millimeters or 6-inch face. And then we have industrial gauges with a diaphragm seal, and we'll talk a little bit more about this, but this is a industrial pressure gauge mounted onto a diaphragm seal. As you can see from a number of gauges we have along the bottom, there are differential pressure gauges, there are gauges with 4 to 20 milliamp output signals. There are many types of gauges out there and a lot of specialty gauges. So if we look at one of the more common specialty gauges, specialty cleaning for oxygen service. So we look at the face of this gauge, we see that it has the no oil symbol on the front. It's indicated that this gauge is intended for oxygen service. The internals are wetted components are 316 stainless steel. A dual scale gauge, it's in bar, PSI, and other information that's important to know about as well as on the face of the gauge. If we look at the side of this gauge, there's a sticker on the gauge that will say that the gauge is manufactured in accordance with ASME B40.100 cleanliness levels, suitable for oxygen service. The dial markings are per ASME B40.100 as well. So in that standard, it would be indicated as to what increments this gauge would be marked off on as per ASME B40.100. Another type of specialty gauge we get into is ammonia gauges. Ammonia, like steam, has a correlating temperature pressure. And if we look at the face of this gauge, we see something interesting. We see that we have PSI on the pressure scale, or inches of mercury in the negative scale. And on the outside of this, we see that that pressure correlates to a specific temperature. And in this case, it's shown in degrees Fahrenheit. So pressure and temperature correlation is shown in a specific specialty gauge, and this is an ammonia gauge. Looking at the gauges, again, case options. There are many different options available, end connections, and typically you'll see the readout in this 270-degree arc marked off as per ASME B40.100, and a few other things about that. If we look at the accuracy scale of pressure gauges, there are various grades of gauges available on the market. And in this case, we're going to look at a 1A, which has a plus or minus 1% of full span. When ASME segments the face of a gauge, it has the lower third, the middle third, and the upper third. Gauges are most accurate in the middle third of the scale. So if we were looking at a gauge we were going to use in 100 psig, for example, we would probably look at a 0 to 160 psi gauge. We would like a gauge operating in the middle third of the scale for greatest accuracy, and it has the least effect on the gauge. If we operate in the upper range, it can start to have an effect on accuracy. It doesn't hurt the gauge to go to that pressure as long as it's not there for extended periods of time at the maximum pressure. So we look at these lower, middle, upper third, and we see that the percentage of span for accuracy is across the full span. So looking at 1A, we have 1% of scale of full span on this gauge accuracy. And as we look at other grades, the accuracy obviously is here. If we looked at a D, it would be plus or minus 5. Swagelok gauges are all in 1A and better. Something else that is often used where you have severe service or you're dealing with pressure spikes. A few things. This is a diaphragm seal or a chem seal, and it has a capillary that is filled with a fill fluid, and there's a diaphragm that separates the process side from the instrument side. And this is welded in. This is a sealed case. So what it does is it protects the pressure gauge from, it can be a temperature buffer, it can be shock, impulse, vibration, there can be pressure spikes, higher temperatures, corrosive suspended solids that you don't want to get in. Remembering that this orifice is a very small orifice, and it's 0.6 of a millimeter if you have a restrictor in there. So it can be compromised if you have a material that may cause clogging, and it acts as a chemical barrier, thermal barrier as well. So mounting a pressure gauge on a thermal barrier or chem seal to buffer it or keep it away from potentially hazardous media or aggressive media, very good idea. If we look at a closer look at one of these diaphragm seals, you can see it's welded. There's a specific fill fluid in the gauge, and this is mounted to an industrial gauge. This has a primary scale only of bar. This is also a compound gauge because it can read negative pressure and positive pressure. Looking at some of the most common gauge failure modes, we look at pressure spikes, overpressure, mechanical vibration. I know I've walked into plants and I've seen gauges that are waving at you and bouncing around here. We get the pulsation also. These are very hard on gauges. Remember, there's a mechanical movement inside the gauge that is made up of segment gears and pinions and very accurate and precise cut movement. So therefore, the wear on that can be exaggerated or can be accelerated, if you will, from any of these types of exposures. Temperature is an issue. We could add a chem seal here. Clogging or corrosion are also issues. Mishandling, putting gauges in areas where they're very susceptible to maybe a fork truck driving past and clipping them. And we see a lot of these things in everyday practice, but these are the 8 most common gauge failures. So what do we need to know if we're going to select a pressure gauge? Well, we need to know the composition of the pressure fluid. We need to know the temperature. What are the ambient conditions this gauge is going to be mounted in? Is it a aggressive area? Is it high temperature? Is there a lot of exposure to salt sprays, or many things? What is the pressure range we want it to operate in? Keeping in mind that the middle third of the gauge is the most accurate. And the conditions affecting wear on the system, the vibration or shock or impulse. Do we need to liquid fill a case? These cases can be liquid filled to dampen the movement inside as well. Do we need to mount a chem seal? What are the methods of mounting that we're going to use with the gauge? And then the required accuracy that your system requires for accuracy. And I'm going to ask now, Phil Daniels, do we have any questions that you'd like to answer for our attendees?
Yeah, thanks, Phil. There are a few questions coming through. So the first question here, I guess regarding gauges, is this type of measurement more reliable or precise than digital sensors? So as with many questions, the answer does depend, especially with precision. But like Phil said, for a Swagelok gauge, most of ours are plus or minus 1% of span. Obviously, if you go to grade B or a grade C gauge, it might go to 1.5 or 2.5. And then if you go to our process gauges, it'll be 0.5% of span, so a bit more accurate. Phil will be touching on pressure transducers shortly, where it's 0.5% accuracy. Or if you use a different method, BFSL, which stands for best fit straight line, it's actually defined as 0.25% accurate. Now, I'm sure if you do need higher accuracy, there are options, but I think the short answer is it does depend on the product you select. Beyond that, we have a couple more questions here. One of them is, what is the system fill fluid? Again, there are many different options, so I'm assuming that question is referring to the diaphragm fill fluid, but the same would apply to the case fill. So depending on maybe the acceptability in the application, sometimes it's the temperature rating. I think that's probably the main driver, but it could be glycerin, silicone, other types of oils. So that is something you would specify based on, your system parameters and especially the compatibility if required. And now I'll put one question to Phil Reid over here. So the question here was about the table for the ASME accuracy, and it mentioned the first, second, and third range. It did appear that there's the same value. So the question is, does this mean that it's just as accurate in the first third or the second third? Or would it maybe mean that there's a different grade for different of the third span? So I'll leave this final question to Phil Reid.
Thank you, Phil. Thank you for answering the questions. What that means is that certain gauges will have a higher degree of accuracy in that center third gauge. As you notice that they all appeared to be the same on the what I was showing. So that's because the gauges that we provide have that level of accuracy across the gauge. But you will still find the highest level of accuracy in the center third of that gauge, just because of the mechanical movement of all the components interacting, the movement, the Bourdon tube. So yes, that I can understand why the confusion on that, but in the gauges that we presented there, the accuracy level is exactly the same across the span. So in that case, 1% of full span. Great question. Hopefully that answered your question. So hopefully we'll answer your transducer question a little bit better here as well. Today we're going to talk a little bit about industrial pressure transducers at a very high level. We'll look at sort of the three most common types: standard, explosion proof, and intrinsically safe. We always ask the question, what is a pressure transducer? A pressure transducer, simply, it's an electronic instrument that converts applied fluid force to a diaphragm, which is converted to an electronic signal that is then sent out to an instrument. It can be a 4 to 20 milliamp signal. It can be a voltage signal as well. But the signal can then be sent to a computer or some other device to correct something or to give digital readings at a location somewhere else. And we'll talk a little bit about that. So transducers are typically used where remote sensing of a system is required, or in a hazardous area where you don't have operators entering the system. We may be 50 meters away from the point that we're taking the pressure reading to where we want to use that. So it's used where remote sensing is desired, or where a higher degree of accuracy is required. And as Phil mentioned, and we will mention it again, the accuracy and the percentage of span. So a transducer is a fairly simple, has a process connection. It has a body that contains all of the electronics, the diaphragm and the Wheatstone bridge, and I'll explain in just a minute. It has a temperature compensating circuit that's all contained in here. And then it has the electrical connection on the outside, which there are many, many options available. There are, I believe, 7 different electrical connections at least, and about 17, I believe, different process connections. I was just going to point out, and it's not clear here, but I'll mention it. We talked about diaphragm seals. This is a diaphragm. This is a flush mount built into the transducer. There can be cooling towers and various other things added here as well, like a pressure gauge, yet the diaphragm is here. So if you had a viscous or a slurry type fluid that you wouldn't want clogging up this process connection, then you would go to a diaphragm. So moving on, a few things about a transducer. It's a thin film and piezoresistive sensing technology. Well, isn't that nice? So we'll talk a little bit about that. It's an all stainless steel construction. It's got temperature compensation for accuracy under various temperature conditions and available with standard explosion-proof, intrinsically safe models. And some of the performance advantages of a transducer is the stability, long-term repeatability, and accuracy. It also provides a great deal of design flexibility with all the various end connections, electric signals, the connections. So it's very adaptable. I do want to talk a little bit about the thin film diaphragm. So this is a diaphragm shown, and it has a sensitive Wheatstone bridge, and it's just a Wheatstone bridge because Charles Wheatstone invented it. And it's made of a stable metal, and this thin film is deposited, and it's like a strain gauge. So as we apply a fluid force to the circuit, and as it starts to deform the circuit, and as we have current flowing through here, it represents a different value, and then is compared to a second circuit that then transfers that into an electronic output that correlates to a pressure. So a little bit more about why we use this technology. It's very stable, very reliable, and very accurate. Long-term stability is equal to or less than 0.2% of span. So when we talked earlier about the percentage or accuracy between digital and mechanical devices, this may answer the question. Also, the repeatability of span, it's equal to or less than 0.1% of span, so very high repeatability and accuracy. Accuracy is equal to and less than, or pardon me, equal to or less than 0.5% of span, and it has temperature compensating circuits in it, so it will compensate for temperature variations. Has a very great, excellent shock resistance and very stable in harsh conditions. So let's take a look at just in general the types of models that are available. So a general industrial application, process controls, labs, test equipment, where it's not in a hazardous environment, not exposed to various elements of the environment. We can look at the E model, which is specifically designed to meet durability and performance demands in industrial applications, where there's explosion-proof requirements. And some of those areas would be things like oil wellheads and petrochemical offshore oil and gas measurement. And then the intrinsically safe model, where you have hazardous environments such as gases, vapors, or dust. So intrinsically safe models are available as well. What do we need to know, or what is some of the critical information when we're selecting a transducer? We need to know the pressure range. What pressure range will the transducer be working in? What are the units of measurement? What type of output signal is required? Do we have a power supply available? Remembering that a pressure gauge is a mechanical device and a transducer now requires a power source. Electrical connection requirements. Again, we mentioned there are 7 different electrical connections available. Connections to the pressure source. Again, we mentioned there are several different sources. And what is that? What is the media like? Is there any special requirements? Do we need a diaphragm? Is there suspended solids? Do we have temperature involved? So many different questions we can ask ourselves. And at this stage, I'd like to open it up. And Phil, do we have any questions?
Yeah, thanks, Phil. We do have a few. I'll use the likes that people have been adding to the questions to drive what we start with. So the first question here is, how do Bourdon tube gauges tend to handle vibration or high shock? Do they tend to be fairly resilient, or can the calibration drift? So as Phil mentioned, it is a sensitive piece of equipment, and the risk when you do have high shock or high vibration is that you could work harden and then obviously affect the accuracy. So typically, if it's low vibration, you shouldn't have an issue. But if you do think that there is high vibration or a high risk of shock, there are things that you can use. So commonly used in steam systems, you'll see a coil or a steam siphon that can protect from a bit of that surge or that shock in the system. Additionally, there's snubber fittings. So often these will have sintered elements, or even using a diaphragm like we talked about, really just to slow down that flow or that shock, because the pressure will still be read and you may have a slight delay, but really that shouldn't be an issue in the system. So again, there are many options you can use to address that. A second question we have here are temperature ranges for diaphragm gauges. So again, this will depend on what you select for the system, but there are a variety of fill fluids, and as well you need to look at the material of the diaphragm, especially the seals. So looking at the gasket material, it could be a Buna or a Viton or a Teflon, so those might have limitations. However, if you go with an all-metal version, that may not be the limiting factor. It may instead be the fill fluid. So on the more limited range, if you go with a standard glycerin, it has a very limited low temperature range to positive 60 Fahrenheit. And then all the way to the other end, there's different grades of silicone. So for diaphragm specifically, silicone low temperature fill fluid could go all the way down to negative 130 Fahrenheit. So again, there's probably a dozen or so common other options, but there is a range depending on what your system requirements are. And then one of the other questions here, mentioning about pressure gauges and recalibrations. So that is something that we can offer. We work with test labs that do recalibrate. The requirement is often dependent on the application or the company, but it's common practice to recalibrate your gauges about every 12 months. So they do come calibrated from the factory, and there are calibration certificates available if required at time of order, but that is something that is commonly done on a regular basis.
Thank you, Phil. So we're going to take a look at variable area flow meters. And a variable area flow meter is quite often a glass column, tapered tube. We have armored versions available, but let's take a little closer look at what a variable area flow meter is. And simply put, it's a measurement device that operates on the principle of allowing a fluid flow to pass around a float in a housing, and it's typically a tapered tube, the housing, and we'll see a picture of that in a minute. And then as the flow force increases, normally from higher flow rates, obviously, the float moves up the tapered tube and allowing for more flow around the float. And as you have this float moving up the tapered tube, variable area flow meter, orientation is important that the flow meter be mounted in the vertical condition. I will give you an option later for mounting a horizontal. And you'll see the float has a corresponding output where it would be read on a scale. So it's direct visual indication of flow. It correlates, the float correlates to a specific, a specific flow rate on the scale. Nice part, does not require any external power. Very low setup cost for a variable area flow meter. If you start looking at things like, mass flow or Coriolis or various other flow type meters, they become very expensive. So this is less expensive than most flow measurement technologies. Very simple device, very robust. There's minimal pressure drop in this device as well. So we have our media enters at the bottom. and starts to flow. And as the flow force increases, it pushes the float further up, and this gap becomes wider, known as the annular gap or ring gap, and it's then correlates the increase in flow. So we have some forces acting in here, and how does this work? Well, we have gravity acting. The force from gravity is constant and it's on the float. The buoyancy of the float, it will be depending on the density of the gas or liquid and the material of the float. And then the flow force coming in causes the float to rise, and as it moves up, we get this larger annular gap, so increase in flow. Now, we have all these forces acting in here, and what two things affect these and what changes is density and viscosity will have an effect on the flow meter. So a typical variable area flow meter is calibrated and typically for water and air. Specific gravities are come into play. So as we change any one of these things, we change any of these conditions, we start to get a change in our readings. So density and viscosity, as we saw in the previous slide, are important. So what can affect the density and viscosity is temperature and pressure. So if you are using a different media, various temperatures, etc., we would need to know it. We can offer special calibration. So most of the standard ranges are for air and water applications. And if you have a custom calibration for a different media, at time of quote, one would look at things such as the fluid to be measured, the fluid viscosity and the units, the specific gravity of this media, the fluid temperature, and again, units of measure always, and the fluid pressure, and then the range that we want to measure the flow rate in. So as we look a little closer at these flow meters, typically they're a glass tube, a variable area flow meter. They have what is known as direct viewing, so you can view the media and you get a direct reading. And most are fitted with a metering valve or regulating valve so that you can control that flow rate right at the source. So as you read it, it's got great accuracy. So looking at some of these glass tube variable area flow meters, we offer 6 models in various sizes and accuracy ranges. And as the flow meter gets larger, the accuracy increases. Of course, cost goes up, and the materials of construction. There is one model offered with a plastic flow tube, very economical, non-aggressive media, and these are all glass tube flow meters. Let's look at the M, which is a metal tube flow meter. This again is a vertical flow inlet in the bottom to the top, but this uses a magnetic interface because we have a metal flow tube. This is able to be offered in a horizontal model, and this is typically at the industrial sector or process plants, those types of things. This model can be mounted in a horizontal, as mentioned, but once again, there's typically 4 models available, some of them with an LED, and again, across the industry, these are very common traits. So as size, accuracy, cost, end connections, what type of end connections, then the orientation, whether you can mount it vertically or horizontally. And as mentioned, we have one model that can be mounted in the horizontal, very highly accurate. It can have limit switches added, and there's many other options available in flow meters as well that could be talked about. And so if we were to have this hooked up, we could have a 4 to 20 milliamp output signal going to an optional readout somewhere else in the system. Has a very big adaptable, very big offering. It's highly configurable, and many options available for these flow meters. A couple other things that are quite common is we provide limit switches in a variable area flow meter, and these have magnetic contact switches in them, and as the float passes, you could choose the 20 as the high and the 4 milliamp as the output for your low. And again, there's a junction box would be required. So these can be dressed and made to suit your application and selected. So what do we need to know with a variable area flow meter? We need to know the fluid to be measured, the viscosity, specific gravity, pressure, the measurement range and units of measure. What type of connections? Remembering that, you know, these have to be mounted in a vertical position unless you buy a horizontal model in the one, and this would have a spring return for the flow. A spring compensates closing or bringing the float back into position, and uses mechanical interfaces, magnetic. And then are there any special requirements or options as we talked about? Very brief overview of variable area flow meters. And with that, Phil, do we have any questions from the attendees?
Yeah, thanks, Phil. We do have a few here. So the first question here is, what's the effect of mixed phases on a gauge or transducer? So the mention is, for example, a liquid pressure in the system, but maybe there's a transducer at a high point and a trap bubble. So to answer this question, from a pressure measurement standpoint, there really is almost no effect. If you even think about a diaphragm gauge that we were chatting about, even in that case, you have a different, you know, let's say your chemical process, and then you would have, let's say, a silicone fill fluid. So even though you have different fluids, whether it's a gas or a liquid, they are pushing on each other and transferring that pressure because it is a balance in the system. So the same would apply if you do have liquid or gas or a mixture. From a pressure standpoint, the system should be at a pressure equilibrium, so that shouldn't have an effect on the actual pressure measurement. Alternatively, the next question here is about a variable area flow meter, whether it can be used with gases and liquids, and what about a mixture. So it can be used for gases or liquids, but as Phil mentioned, it is critical to know the density or the viscosity or the fluid itself. So each flow meter is calibrated to a specific fluid and a specific set of conditions. So commonly you would be air at ambient conditions, or if you have a specific fluid or specific set of conditions, we can calibrate it. But if you do change from one to the other, you would need to have it recalibrated or reset. Same thing for a mixture. Again, it depends on if there's consistency. So when you have a mixture of gas or liquid for a variable area, that could have some inconsistencies depending on if it's measuring more gas or more liquid. So that may not be ideal for that situation. Once I'm done wrapping up here, I'll let Phil comment on that as well. And then the third question here is about capillary connection, comparing that to a cooling tower. So I think either would be suitable for different applications, depending on, you know, how much cooling you have, things like that. Even within cooling towers, there's different methods, different lengths. So I would think that depending on what your application conditions or what your fluid are, it just depends on how that lines up with the capabilities from a capillary, or you know, what's that level of cooling that you would experience from different types of cooling towers. Phil, did you have any other comments about mixture of gases measuring in a flow meter or about capillaries?
No, Phil, that was a good explanation. The density and specific gravities are important in a variable area flow meter, and so therefore, if it were consistent, but if it's changing, then you would have some inaccuracies. Again, because of the calibration of it from the specific media that it was calibrated for. So I think you answered both those questions, Phil. Thank you. We're going to move on. We will come to mechanical temperature measurement products, bimetal thermometers. And so what is a bimetal thermometer? It is a thermometer consisting of a stem and a helically wound bimetal strip, which is welded at one end. It has a staff wire that goes up to a pointer, and it correlates to a temperature reading on a dial. The wetted components are all welded together to prevent ingress and leakage. There's usually a process connection, and this would typically be used with a thermal well so that the stem is not directly into the media. But first, let's take a look at a bimetal thermometer. So with the coefficients of expansion contraction of metals, and using dissimilar metals, they have different expansion coefficients, and bonding these together. And then as we apply a temperature, we apply a heat source to one side, the metal with the lower thermal coefficient of expansion, and you'll start to have a warping effect. It's anchored at one end, and the metal with the higher coefficient of expansion expands at a greater rate. So this expansion contraction, it causes the bonded metal strip to bend proportionally to amount of heat added to it, and then transfers that to an output. So we helically wind these bimetal strips, and again, it is proportional to the movement of the strip to the pointer on the output. So as we add heat and this starts to feel those effects, we start to see the dial, the pointer indicating on the dial hotter or colder. And so the whole system is helically wound and heat treated for a long life. So this helically wound bimetal strip is has a very long, stable life. So if we take a little closer look at this thermometer, we see the stem, as we talked about, and inside the stem we have the bimetal strip anchored at one end, the bimetal helix. Then we have the staff wire connected to that helically wound bimetal strip going up to the pointer, and this is all sealed. These cases are all sealed and hermetically sealed so that there's no ingress and you'll get no fogging of the lens as well. I might add that these stems can be 2 to 72 inches in length. They also have an adjustable movement in them that is adjustable on the case, and we'll talk about that in just a few minutes. It has a lens and a pointer. The lens material can be various materials. It comes with instrument glass, but you can have a polycarbonate or a laminate glass also available. The case is 304 stainless. It has this 304 bezel holding this lens with a gasket in here, so we have it hermetically sealed. And the maximum ambient temperature for the case operating is 95 C or 200 degrees Fahrenheit. So as we look at this hermetically sealed case I mentioned earlier, this is in accordance with ASME B40.200, so that it's sealed up so that we are able to get accurate readings. There's nothing worse than trying to look through a fogged up lens at something. So that's taken into account. Also, the anti-parallax of these specific thermometers. So you're reading on the same plane with this anti-parallax where the numbers, the dial graduations are here, and the pointer is at the same plane. If you had two planes, you'll get what's called parallax. You may be reading plus or minus somewhere on that reading. Also, the thermometer is able to be field adjusted for accuracy. It has that can be traceable back, and there's a slot and adjustment screw on the back with a geared face. So what actually happens is we turn the adjustment screw on the back. It actually rotates the lens inside, and so that the pointer for accuracy. And the way you would do that is you would usually take either agitated ice water or boiling water. You would need a calibrated thermometer with a higher accuracy rating and traceable, and do the comparisons, and using the adjustment screw you would align the output to the known. Also, we have a dampened movement, which minimizes that pointer oscillation if you have a vibration or shock or impulse without filling a case with liquid media. And it gives the benefits of a liquid fill in a dry case. Also, accuracy, similar to gauges, transducers, flow meters, there's an accuracy range. And if we look at the thermometers and the Swagelok bimetal thermometers have an accuracy of plus or minus 1% of full scale, and that's in accordance with B 40.200 accuracy specifications. And so across the full scale, you'll see that the Swagelok thermometer maintains accuracy across the full span. So it maintains that plus or minus 1%. And similar to the gauges, the midpoint, and as we start to get out into different grades of accuracy, the accuracy starts to wane. We start to get a much broader range. So all of these bimetal thermometers from Swagelok are grade A with a plus or minus 1% of accuracy of span. So again, all that means is that if we had a thermometer 0 to 250 or minus 20 to plus 120C, the accuracy of plus or minus across scale 1% would be 2.5 degrees Fahrenheit on full scale, anywhere along that measuring range. Options, there are types of mounting, center back, lower back, and then adjustable mounting is available so that you can get your thermometer on the right plane. Also, something else that would typically be used with a thermometer are Thermowells. Thermowells can be ANSI flanges, threaded, diaphragms, or sanitary clamp. And these are simply threaded into the connection, then the thermometer would be threaded into the Thermowell to protect that stem. And these are very rigid. They're machined from stainless steel. Typically, there are other alloys available. But also, you can remove the pressure gauge from the system without isolating or draining down the system. This is the pressure boundary, and then the thermometer is mounted into the Thermowell. So it just protects the device from the process media. Keeps it from contamination in the process fluid. And again, very broad temperature measurement devices can easily be removed from the system by simply threading them out. If you have insulation, you can have pipe lagging, which allows you to add installation and puts that thermometer out 2 to 4 inches out from the actual connection. And these can have many different options: threaded, ANSI, quick clamp, and typically there's 3 different designs. There would be straight, reduced, and tapered, used for different applications and different process media. And so a few of the things we need to know when you're selecting a thermometer would be fluid temperature range to be measured, the dial size required, units of measure and the scale, the length of the stem. Remember, I mentioned it can be anywhere from 2 to 72 inches in length. And how are we going to connect to the temperature source that we're reading? Is it a NPT? Are we going to be ANSI flanged? And then any special requirements, options, any specific certifications, calibration, and always remember the Thermowell and process connection are important. And with that, Phil, do we have any questions on mechanical temperature measuring devices?
Yeah, thanks, Phil. We do have a few more questions. Again, thanks to the group. We're getting a lot and some great questions, so appreciate the input from the group. I'll start here, back to the rotometers. So it says, for an unknown gas mixture, what's the error anticipated if you have one, say, calibrated for nitrogen? So the short answer is it can be very drastic. So if you have something very similar, like it's calibrated to air and you're using it for nitrogen, it may not be that substantial. But if you look at something like hydrogen, you could have a 400% error in accuracy. So it is critical to make sure that you know your gas mixture and then understand what the difference is based on the calibration. Beyond that, another question here, what is the recommended frequency for recalibrating flow meters? I'll leave that to Phil Reid to address what his experience is on that. Another question here, do you sell non-contact flow meters? So there are standard catalog items. So if you do something or you have a request for a non-standard, please reach out. Swagelok does have some non-standard items, whether it's something like this flow meter, special alloys, high temperature. So please reach out to your local distributor. Swagelok does always have some special offerings. Then we can look at it case by case. And then the final question here, Do you have a thermocouple, RTD, or other electronic temperature measurement? I believe we do have a couple options that are more specialized, but again, primarily we do have the temperature measurement with the thermometers, but we do have some options within our supply chain that we can support you with. So maybe I'll leave it to Phil to add any comments about that final question or about the calibration for the flow meters.
Yeah, thanks, Phil. When it comes to a flow meter, typically they don't go out of calibration. That is dependent on the media being used, so the viscosity, the densities, and specific gravity. Unlike pressure gauges, that typically a pressure gauge is calibrated annually. We have some customers that actually calibrate quarterly, and that again would be dictated by QA, ISO, other things. But going back to the variable area flow meter, typically it's not calibrated. Once a year, accuracy can be checked for in that specific media, but it's typically not a device that gets the variable area flow meter is typically not calibrated on a regular basis. But again, items like thermometers, transducers, and temperature gauges do need calibration on a regular basis simply because of the way they move and their characteristics. Okay, with that, thank you all for attending. We have a group that's available, and any of the sales and service centers around the globe are capable of helping you, and we can help you direct to those people. And they will all have a team of engineering support specialists there to give you a helping hand. And here we have a few of ours on the screen that are readily available in our service area to provide you with help. And with that, I'd like to thank you all for your time and your great questions. If there's any feedback, please provide that to us. I believe Tim will be sending some information to each of you that registered, or reach out to myself or any one of our team or any one of a team member at any of the 200 locations around the world that we mentioned, and we would be very happy to help you. And again, thank you very much for attending, and have a great day.